Greetings, ladies and gentlemen. In our previous lecture, we talked about linear combinations, and basically we said if we have a vector space V, then we can easily write any element of V. For example, if we take an element V from our vector space V, then we shall say that we can write this V as a linear combination of other vectors u1, u2 up to um, such that we have V equaling to alpha 1 u1 plus alpha 2 u2 plus up to alpha m um. So if there exists scalars alpha 1, alpha 2 up to alpha m, such that we can have alpha 1 u1 plus alpha 2 u2 up to alpha m um equaling to V, then we shall say that V is a linear combination of the vectors u1, u2 up to um. So our major interest is to write or to obtain the values for alpha 1, alpha 2 up to alpha m, such that we are able to write this expression here. So we want to come at some other more examples about linear combinations before we look at something new. So let us talk about this example here. The example says we need to write the vector W, which is given as 1, 1, 1 as a linear combination of the vectors in this given set. So how do we do that? We are given W, vector W. So we have our vector W, which is 1, 1, 1. We need to write this one as a linear combination of the vectors which are in the set S, and set S contains 1, 2, and 3, 0, 1, and 2, then negative 1, 0, and 1. So to write W as a linear combination of these vectors, so what we need is, we need to find the scalars. We need to find the scalars alpha 1, alpha 2, and alpha 3, such that we are able to write alpha 1 into 1, 2, 3 plus alpha 2 into 0, 1, 2 plus alpha 3 into negative 1, 0, 1 to be equal to W, which W is same as 1, 1, 1. So in order to write W as a linear combination of these vectors here, if this is your U1, this is your U2, and this is your U3, so you seek the scalars alpha 1, alpha 2, and alpha 3, such that you are able to write alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3, and this must be equaling to our vector W. So if we are able to get alpha 1, alpha 2, and alpha 3 such that this is equal to W, then we shall say W can be written as a linear combination of these vectors U1, U2, and U3. So let us look at how best we can obtain alpha 1, alpha 2, and alpha 3. So this can be easily written as alpha 1 into 1, 2, 3 plus alpha 2 into 0, 1, 2 plus alpha 3 into negative 1, 0, 1, which is equal to 1, 1, 1. We can as well write this when we add the corresponding components alpha 1, then plus this is 0 alpha 2, so it will be plus negative alpha 3. Then when you multiply alpha 1 with 2, we shall get 2 alpha 1. Then add there the corresponding component here is plus alpha 2. Then this is alpha 3 times 0, which is 0. But the whole of this is equal to 1, 1, 1. So when we multiply also this one here, we shall get 3 alpha 1. This is plus 2 alpha 2 plus alpha 3. So let us equate the corresponding components. Equating the corresponding components, we shall have equations alpha 1 minus alpha 3 equaling to 1, 2 alpha 1 plus alpha 2 equaling to 1, and lastly 3 alpha 1 plus 2 alpha 2 plus alpha 3 equaling to 1. Our major interest here is therefore to use any method for solving for the unknowns alpha 1, alpha 2, and alpha 3. Let us use a Gauss elimination method. So if we try Gauss elimination method, we shall have to get the augmented matrix. So the augmented matrix will be, so we shall have 1 here, 0, negative 1. Then this side we shall have a 1. This will be 2, 1, and this will be 0. Then this will be 3, 2, and 1. This is 1, 1. So let us try to use row operations to solve for this given system. So having this, we can now apply what we call the operations and see what best we shall come with. So let us apply the operations. So we have our matrix, which is 1, 0, negative 1, 2, 1, 0, 3, 2, and 1. Then having 1 here, 1, 1. So we need to apply row operations. So if we want to eliminate this, we shall apply negative 2 in row 1. We add there row 2 to give us row 2. Still we can apply negative 3 row 1 plus row 3 to give us row 3. So here we are maintaining 1, 0, negative 1, and 1 constant. Then we shall have negative 2. Let us multiply negative 2 in this one here. We shall get negative 2 times 1 plus 2. This will give us a 0. Negative 2 times 0 plus 1. This one will give us 1. Let us again get negative 2. We multiply it by negative 1. We add there. This is 0. So we shall obtain this as 2. This is positive plus 0. So we shall have a 2 here. Then we get negative 2, multiply it in 1. Then add there this 1. And this will give us negative 1. So we shall have a negative 1 there. Similarly, we shall have a negative 3 times 1 plus 3. We are on this row. Negative 3 times 1 plus 3. This will give us 0. Negative 3 times 0 plus 2 will remain 2. Then negative 3 multiplied in negative 1, add there this 1. and this will give us a 4. Then next we shall have negative 3 multiply it with 1. Then add there this 1 here, we shall get negative 2. So we shall have a negative 2 there. So basically we shall have this one here as our operation. So looking at this, we can also try to eliminate this one here by using negative 2 in row 2 plus row 3 to give us row 3. When we do that, we shall have to maintain 1, 0, negative 1 together with this one here, 0, 1, 2, then negative 1, then this will be 0, so we are getting negative 2 times 1 plus 2, it will also be 0, negative 2 times negative, this is negative 2 times 2, negative 2 times 2 plus 4, it will also give us 0. Looking at the next one, we shall have negative 2 times this negative 1 here plus negative 2. This is positive 2 minus 2, which will give us 0. So we shall have a 0 there. So looking at that, we shall have our system as 1, 0, negative 1 and 1 here. We shall have 0, 1, 2, negative 1, 0, 0, 0 and 0. So when we look at this, we can see that this is now in row echelon form. So what we can do, we get the corresponding system. So the corresponding linear system is, we shall have this as alpha 1, then plus 0 minus alpha 2, this is minus alpha 3, equaling to, this is 1, then this one here, this is alpha 1, alpha 2, alpha 3, then this will be alpha 2 plus 2 alpha 3 equaling to negative 1. Then the last one is 0, 0. So basically we need to expect infinitely many solutions. So what we can do here, we can relate one of the parameters. We can easily see that we have alpha 1, alpha 2 and alpha 3, but we have only 2 equations. So we shall relate alpha 3 to be a free parameter to bt for t which is from R. So for that case, we shall have alpha 1 minus t is equal to 1. So meaning alpha 1 is same as 1 plus t. When we look at alpha 2 plus 2t will give us negative 1, meaning that alpha 2 is same as negative 1 minus 2t. We have so far obtained the values for alpha 1, alpha 2, alpha 1, alpha 2 and alpha 3, but we can easily see that these values for alpha are in terms of the parameter t. So this implies that our system, this system has infinitely many solutions, each of the form we have clearly seen that alpha 1 is same as 1 plus t, alpha 2 is same as negative 1 minus 2t, and alpha 3 is same as t. That is what we have so far done. So, since this system has infinitely many solutions, we can choose any one of the solutions. Now, let us suppose let us say to obtain one solution. To obtain one solution, we can let t to be like 1. And then it will imply that alpha 1 will be 1 plus 1, which is equal to 2. Alpha 2 is same as negative 1 minus 2 times 1, which is same as negative 3. And alpha 3 is same as 1. So this will clearly imply that W can be written as 2 into 2 into, so we had our vectors 1, 2, 3 minus 3 into 0, 1, 2 plus 1 into negative 1, 0, and 1. So these were the vectors that we had. So clearly, we have got our alpha 1, we have got our alpha 2, and we have got our alpha 3. So meaning that we can easily write the vectors in S, which is 1, 2, 3, 0, 1, 2, negative 1, 0, 1 as a linear combination of this W. So that is how we treat vectors which will give us a solution that has infinitely many solutions. Meaning, someone can let t to be 1, someone can let t to be 2, t to be 3, or any other value. So any value that you obtain should be able to give you alpha 1, alpha 2, and alpha 3. So after getting alpha 1, alpha 2, and alpha 3, then you can write this given combination. So in case this is your U1, this is your U2, and you have let this to be your U3, so you can rate you can conclude with W as 2U1 minus 3U2, then plus 1 times U3. Let us talk about example number 3. In example number 3, we want to see if it is possible that we can write this W, which is 1, negative 2, 2, as a linear combination of the vectors in the set S. Set S is the set that we have so far considered in our previous example. So this set S is this set having these vectors. So we want to see if W changes but S remains the same. Can this W that we are having 1, negative 2, 2 be written as a linear combination of these vectors here? That is what we basically need to look at. So let us look at how best we can do that using the similar method that we have so far looked at. So our major interest is to show that W can be written as a linear combination of these vectors here. So what are the vectors? We have these vectors which we can call as U1, U2, and U3. So what is our interest? We need to show that there exists some scalars alpha 1 which we can multiply with U1 plus alpha 2 U2 plus alpha 3 U3, and this is equal to W. If we are able to get these scalars alpha 1, alpha 2, and alpha 3 such that this expression holds, then we shall say W can be written as a linear combination of U1, U2, and U3. So following the similar case as we did in our previous example, let us try to simplify this expression here. So we have alpha 1 into this, alpha 2 into this, alpha 3 into this equaling to. So clearly we shall have alpha 1 multiplied into this, you add there this, plus this one here. So the corresponding augmented matrix, so the augmented matrix will be, so the augmented matrix is actually the same. Otherwise, the only thing that changes will be this constant matrix here, that is the matrix on our right hand side. So that is negative 2 and 2. That is the only matrix that will change, but our previous matrix will still hold. That is the matrix of coefficients. So we shall have 1, 0, negative 1, shall have 2, 1 and 0, then we shall have 3, 2 and 1. So we shall still use row operations. We shall still use row operations to see whether we can be able to get alpha 1, alpha 2 and alpha 3. So let us use row operations. So we shall have our matrix here, which matrix is 1, 0, negative 1. Then here we are having 1. Then we have 2, 1, 0. Then here we have 3, 2 and 1. So this one here we have negative 2 and 2. So that is the matrix we are considering, this matrix here. So let us use row operations. So we shall apply the first operation. We can consider the operation which is negative 2 in row 1 plus row 2 to give us row 2. We shall consider negative 3 in row 1 plus row 3 to give us row 3. So basically we shall have the first row constant. So negative 2 times 1 plus 2, it will give us a 0. Negative 2 times 0 plus 1, it will remain 1. Negative 2 times negative 1, it will be positive 2 plus 0, it will remain 2. Negative 2 times 1, negative 2 times 1 plus negative 2. Negative 2 times 1 plus negative 2, it will give us negative 4. So next we look at this one here, negative 3 times 1 plus 3, it will give us a 0. Negative 3 times 0 plus 2, it will give us a 2. Negative 3 times negative 3, negative 3 times, this is negative 1, plus row 3, which is 1. So this will be 3 plus 1, which is 4. So we shall have a 4 here. Next we shall look at negative 3 times positive 1 plus this 2, and this will give us negative 1. So we shall have negative 1 here. So next we want to eliminate this 2 here. So we shall apply negative 2 row 2 plus row 3 to give us row 3. So this will give us 1, 0, negative 1. Then still we have here 1. Then this is 0, 1, 2, negative 4. Then the last one will be we are applying this operation. Negative 2 in 0 plus 0 is 0. Negative 2 times 1 plus 2 is 0. Negative 2 times 2, negative 2 times 2 plus 4. It will also give us 0. Then this will be negative 2 times negative 2 times negative 4 plus negative 1. So this will be same as 7. So we can clearly see that when you look at this last row, the last row is actually showing that the system is inconsistent, because when you look at 0 equaling to 7 does not exist, because when you get back the linear system, you realize that 0 equaling to 7 does not exist. So we can give the conclusion. It can give the conclusion that it is not possible to get the values for alpha 1, alpha 2, and alpha 3, such that we are able to write W as a linear combination of U's. So we can say from the third row, this one here, from the third row, we conclude that the system of equations is inconsistent, which means that there is no solution, for alpha 1, alpha 2, and alpha 3. Consequently, we can say W cannot be written as a linear combination of U1, U2, and U3. So if you find that the system is inconsistent, then it means you cannot write a given vector in terms of a linear combination of other vectors. We now talk about a spanning set of a vector space. So when do we say that a given set spans a vector space? So we shall consider a set which is having vectors v1 up to vk, which is set S. So this set here, which is a subset of a vector space V, is said to span V, or it is said to be a spanning set of V, when every vector in V, that is, if you are able to pick any vector from V, and this vector V can be written as a linear combination of these vectors here, then we shall be able to say that this set here spans a set V. What do we have here? We have a given vector space V. We also have a subset which is containing some vectors v1, v2 up to vk. Then we shall say that this set here spans this vector space when we are able to find any vector in V, which is V for example, such that we can write this V as a linear combination of these vectors, that is alpha 1 v1 plus alpha 2 v2 plus up to alpha k vk. So if you are able to get any vector from this given set V, such that you can write that vector as a linear combination of the vectors in this given set, then we shall say that this subset here spans this given vector space. So in other words, every vector from this V must be written as a linear combination of the vectors in this set S. If that can be achieved, then we shall say that this set spans a vector space V, or S is a spanning set of V. Let us look at some few examples so we can see how best that one works. Now, let us consider vectors V1, V and V2. So we are saying suppose V1 and V2 are given as that. So we need to show whether the given set containing V1 and V2 will actually span R2. So let us look at what we can basically do in order to show that. So we shall say we are given the vectors V1, which is 1, 1, V2, which is 1, negative 2. We need to show that the set S, which contains V1, V2, this set here, whether this set here spans the given space, which is R2. So this is what we need to show. So to show that this set here spans R2, it means that any vector you pick from R2 should be expressed as a linear combination of these vectors V1 and V2. Let us suppose, let a given vector be picked from R2. Since R2 consists of elements of the form xy, we shall also let our V to be in form of x and y. This is R2, so there should be 2 entries. Now, if we pick V from R2, we need to show that this V can be written as a linear combination of these vectors. In other words, we need the scalars alpha 1 to be multiplied with V1 and alpha 2 to be multiplied with V2. So if this is possible, then we shall be able to say that this given set spans R2, because any arbitrary vector or any vector you pick from R2 can be expressed as a linear combination of V1 and V2. And R2 is of the form x and y. So we have picked any vector V from R2, and we need to show that this vector can be written as a linear combination of the vectors in S. So let us now get the values of alpha 1 and alpha 2. If it is possible, if alpha 1 and alpha 2 have got the solution such that this can be written, then we shall say that V, that is this set here, spans R2. So let us start. We have xy equaling to, this is V, because vectors in R2 are very many, but they are of the form xy. So that's why we have picked a general vector xy. So this is alpha 1 into V1 is 1, 1, alpha 2 into -1, -2. So we can easily write this as alpha 1, that is when we multiply this one here, plus this is alpha 2 minus 2 alpha 2 equaling to xy. We can get our system as alpha 1 plus alpha 2 equaling to x, then alpha 1 minus 2 alpha 2 equaling to y. We need to solve this system and get the values of alpha 1 and alpha 2. So let us use the row operations. So we need the augmented matrix. So the augmented matrix is so we can have the augmented matrix as 1, 1, 1, negative 2. Then here we have x and y. So let us try to use row operations and see whether we can get the values of alpha 1 and alpha 2. So we can apply a negative row 1 plus row 2 to give us row 2. And this will be 1, 1. This is x. This is negative 1 plus 1. This is 0. Negative 1 plus negative 2. This is negative 3. Negative x plus y. We have negative x plus y here. So next, we have so far obtained 1, 1, 0. This is negative 3. Then this one was x. Then negative x plus y. So next we need to create a 1 here, so we can apply negative 1 over 3 row 2 to give us row 2. So this will be same as having 1, 1. This is x, 0. This will be 1. Then this is negative a third into negative x plus y. So this will also give us, so since we have already put this one in echelon form, so we can get the corresponding system. Remember, this is alpha 1, alpha 2. So we can have alpha 1 plus alpha 2 equaling to x as one equation. Then alpha 2 is same as negative a third into negative x plus y. We can have that. So let us substitute from star. We have alpha 1, which is equal to x minus alpha 2, which is same as x minus alpha 2 is a third into negative x plus y. This will give us LCM is 3 divided by 1, 3x, plus 3 divided by 3 is 1. This is minus x plus y. So this will give us 2x plus y divided by 3. So we can write this as a third into 2x plus y. This is alpha 1. So it is clear that we have got alpha 1 and alpha 2. For example, you say that let me take my x to be, for example, 4 and y as negative 2. If you do that, what do you think will happen? Alpha 1 is same as a third. So this will be same as a third into 2 times 4 minus 2. This is same as a third into 6, and this will give us, for example, 2. If you need alpha 2 we had obtained that as this, that is negative a third into negative x plus y. So clearly this will be negative a third into negative 4 minus 2, and this will be same as negative a third times negative 6, and this will give us 2. So it is very clear that for any values of x and y, that you will have, you'll be able to get alpha 2, and alpha 1. So that is, for our case, we have taken for the case if x is equal to that, but someone can take any other values. But for any values of x and y, but remember x and y represent v. So our v was x and y. So in other words, you are able to get your v as 4 and negative 2. So the moment you have v, you can easily get alpha 1 and alpha 2. So in case you have your v as that, so it means you are able to write v as alpha 1. Remember, it was alpha 1 v1 plus alpha 2 v2. This is what we had. This is what we had here. So it is clear that now, since we have obtained the values of alpha 1 and alpha 2, so we can easily write v as a linear combination, because v will be 2v1 plus 2v2. So you can easily see that for any v that you pick from R2, you can be able to write a v as a linear combination of v1 and v2. But remember, this was S. So if this is possible, we therefore say that S spans R2. Okay, so that one is, I hope that one is very clear. So what was your interest? Your interest is to get or to show that alpha 2 and alpha 1 exist. And if they exist and they have got a solution, you should be able now to conclude. So what will be our conclusion based on this? So our conclusion will be that V1, V2, this set here spans R2, since for any vector V, you pick from R2, we have alpha 1 and alpha 2 such that V can be written as alpha 1 V1 plus alpha 2 V2. So having shown this, that alpha 2 can be easily obtained as this, then we can give this conclusion. But now let us look at the case, in case this would not be possible. For example, in case here you have a 0, then it means your system has got no solution. And if it has no solution, then clearly you cannot write that V as a linear combination of V1 and V2. Let us talk about example number 2. Suppose V1 is given as 1, negative 2. V2 is given as negative 2 and 4. Then we need to show whether this set here spans R2. So in order to do that, we shall need to pick a vector from R2. Then we show that this vector from R2 is a linear combination of these vectors. We know how to deal with a linear combination at the moment. So for that case, let us have So we are given V1 as 1, -2. We are given V2 as -2 and 4. So we need to show that the set V1, V2 spans R2. So if this set here spans R2, then you must show that when you pick a vector from R2, which vector we can call vector V, and that vector should be in form of xy. So if we have a vector, any vector from R2, for example V, then we shall need to show that this V can be expressed in terms of the linear combination of the vectors V1 and V2. So we need to show that this V here can be expressed as a linear combination of V1 and V2. Can be expressed as a linear combination of V1 and V2. So in order to do that, we shall need to have scalars. So this will imply we need scalars alpha 1 and alpha 2 from the set of real numbers, such that we are able to write alpha 1 V1 plus alpha 2 V2 equaling to this V. So we need to show that this V can be written as a linear combination of V1 and V2, and for that case it means there exists some scalars alpha 1 and alpha 2 such that we can write this. So in case we get the values for alpha 1 and alpha 2, then we can easily say that V can be written as a linear combination of V1 and V2. But if we are not able to get the values for alpha 1 and alpha 2, or if this system here does not have any solution, then we shall conclude that this vector V cannot be written as a linear combination of V1 and V2. So let us look at that. Alpha 1 into what is V1? V1 is 1, -2, plus alpha 2. Alpha 2 is multiplied into -2 and 4, and this is equal to x and y, that is V. So this implies that we shall have alpha 1, then -2 alpha 1, plus -2 alpha 2, then 4 alpha 2, which is equal to xy. So we can have this as a system that is alpha 1 minus 2 alpha 2 equaling to x, and -2 alpha 1 plus 4 alpha 2 is equal to y. We can have an augmented matrix corresponding to this system. So the augmented matrix is 1, -2, then x, -2 and 4, then y. So we need to use row operations and see whether this system here has got the solution or not. So applying row operations, let us rewrite our matrix. Our matrix is 1, -2, -2 and 4, then x and y. So we can use the operation 2 in row 1 plus row 2 to give us row 2, If we do that, we shall be able to get 1, -2, and x. Then 2 times 1 plus -2 will be 0. 2 times -2 is -4, plus 4 is 0. 2 times x plus y, it will give us 2x plus y. Clearly, you can easily see that you have 0, then 2x plus y. So what does that one imply? That this system here has no solution. So we cannot get the values of alpha 1 and alpha 2. We cannot get the values of alpha 1 and alpha 2 such that we can express this v in terms of v1 and v2. So if the system has no solution, so we can therefore say this system here is inconsistent. Therefore, from row 2, we conclude that the system is inconsistent. The system is inconsistent, and therefore from row 2 we conclude that the system is inconsistent and hence no solution. And if that is the case, clearly no values of alpha 1 and alpha 2, clearly we shall have no values of alpha 1 and alpha 2 such that alpha 1 v1 plus alpha 2 v2 will be equal to v. So we cannot get the values of alpha 1 and alpha 2 such that we can write this expression here. And if that is the case, then we conclude that this set here, which is our set containing v1 and v2, does not span R2. So therefore, from row 2, we conclude that the system is inconsistent, hence no solution. Clearly no values of alpha 1 and alpha 2 such that this one happens. So therefore, the set containing v1 and v2 does not span R2. So that is how we can prove that this set here spans R2. So if it spans, you should be able to write any vector from here as a linear combination of these vectors, meaning the solution must exist. If it does not, then you conclude that the given set does not span that given vector space. We talk about some more examples. Example number 3, you should be able to try it out. So you need to show whether U1, U2, U3, and U4 will span R3. So you should be able to pick any vector from R3, and you should be able to show that this vector can either be written as a linear combination of these vectors U1, U2, U3, and U4 or not. In case the vector from R3 can be written as a linear combination of the vectors in U as U1, U2, U3, and U4, then it means these vectors will span R3. But in case you cannot obtain the values for the unknowns, or if the system will have no solution, then you will conclude that these vectors don't span this given set. Then the next question says find all the possible values of lambda such that this one here is in the span of this. If this vector is already in this span, it means this vector can be written as a linear combination of these vectors here, because they are saying this one is in the span of this. So let us try to write or to look at the values of lambda, for which we shall write this vector here as a linear combination of these two vectors that we are given, because this vector is already in the span of this, which means that the values for alpha, or the values of the unknowns, exist. So let us look at how best we can solve that. So we are given the vectors, we are given the set of vectors, which vectors we have 2, 0, 4, negative 1, 3, and 2. Then we also have 1, lambda, and 6. And they are telling us that this one here is in the span of this given set. So what does that one mean? It means that this one here can be written as a linear combination of these vectors. So if that is the case, let us look at the solution. So since this is already in the span of this, then it implies that we can write 1, lambda, and 6 as a linear combination of these vectors here. So this will be equal to some scalars, for example, alpha 1 into 2, 0, and 4 plus alpha 2 into negative 1, 3, and 2. So you are indirectly showing that this one here can be written as a linear combination of this. So that's why we are saying we equate this one here to alpha 1 into this plus alpha 2 into this. So that is the meaning that this one is in the span of this. So in other words, you want to show that this vector can be written as a linear combination of these vectors here. So for that case, we shall have 1, lambda 6 equal to, then you can have this as 2 alpha 1 minus alpha 2. This will be 0, so this will be alpha 3. This will be 4 alpha 1 plus 2 alpha. This is 3 alpha 2. 3 alpha 2. So this will be 4 alpha 1 plus 2 alpha 2. So from there, still we can have this one in augmented form. So we can say the augmented matrix is, so our augmented matrix will be 2, negative 1, 0, 3. Then this is 4, this is 2. Here we have 1, lambda, and 6. So they are telling us that this one is in the span of this, and for that case, it means the linear combination, or expressing this as a linear combination of this one here, is possible, meaning that we must get the solution. So let us try to use operations here. We can also try to make this one 0. We can use negative 2 in row 1 plus row 3 to give us row 3. So for that case, we shall have 2, negative 1, then 1, we shall have 0, 3, and this is lambda. We shall have this one here, as negative 2 times 2 will give us 4, which is a negative 4, plus 4, it will be 0. So negative 2 times negative 2, it will be positive. So that will be positive 2, plus 2, it will give us 4. Then next we shall have this one here. It will be negative 2 times 1, which is negative 2, plus 6, it will give us 4. So that is what we have. So next we can also apply another operation. So we already have 2 negative 1. This is 1. So here we have 0, 3. This one here is lambda. This one here is 0. Then the next one is 0. This is 4. That's referred to this matrix. We are rewriting this. Then the next one is also 4. Then this is also 4. So we can also create a 1 here. So let us take the operation 1 over 4 in row 3 to give us row 3. When we take that operation, we shall have 2, negative 1. This is 1. This is 0. This is 3. This is lambda. This is 0. This is 1. This is 1. So from there, we can now try to also eliminate this value here using this. So let us apply negative 3 in row 3 plus row 2 to give us row 2. So we want the effect in row 3, so to give us row 3. So if we do that, this will be 2, negative 1. This is 1. This is 0. This is 3. This is lambda. Then this is negative 3. This will be 0. Negative 3 times 1, it will be 3, plus 3, it will be 0 here. Then negative 3 times 3, this will be negative 3. This is negative 3 times 1, which is negative 3, plus row 2 is lambda, so we shall have here negative 3 plus lambda. So we shall have this. Now looking at this system here, we can easily see that this system here is inconsistent. But they told us that this system here has to be consistent. So if it has to be consistent, then it means this value here must be equal to 0, because they told us that this one here is in the span of this, which means that the solution to this system here exists. And if the solution exists for that case, it means if we get this one here, it implies the solution or the system is inconsistent. But if the solution exists, then it means this one here should also be equal to 0, because if this is equal to 0, then we shall have infinitely many solutions for that case, and it will be 0, 0, 0, which means the system will be consistent. So we shall say if lambda is not equal to 3, if lambda is not equal to 3, the system, this system here is inconsistent. So for the system to be consistent, it means lambda must be equal to 3. Otherwise, the system will be inconsistent. That is when lambda is not equal to 3. The system will be inconsistent because for any value of lambda other than 3, then if, for example, if lambda is 4, it means this side you have 0, 0, then this side you will have 1, which will mean that the system is inconsistent. But for the system to be consistent, then it means this lambda here must be 3. In other words, when you get -3 plus lambda, you must be able to get a 0 because that's when this system will be consistent. So that's why we are having lambda as 3. So since they have already told us that this system here is consistent, meaning that the solution exists because this one is in the span of this or in the span of this set. So it means that alpha 1 and alpha 2 must exist. And that's why we are taking the case that the system will be consistent when lambda is equal to 3. So therefore the value of lambda will be taken to be 3 for this to be in the span of this.
Yeah.